All right, hopefully we're recording. So me and a couple of the other TAs, I think, are going to be posting a couple videos to help you guys out before your final. If you guys find it's valuable to you, that's all the best. But yeah, I know for me, like sometimes watching other people go through problems is definitely helpful. So we're going to cover a couple of things. I'm going to do two videos. This one will be BVP 10A, and then maybe I'm thinking I'll do BVP 13 or one of those later ones. But yeah, so anyways, I guess we'll get right into it, but feel free to send me an email or anything if you have any other questions. I think the final's in a couple of days, so I'm sure you guys are focused here. But anyway, so BVP 10, it's one of the Sturm Liouville theory problems, and it's actually going to use the Bessel equations. For 10A specifically, it's going to use the modified Bessel's equation, which we'll get into later, but it's definitely a good one to know. I believe this was on my final last year, so I wouldn't overlook it. And anyway, let's get into it. So basically, we're looking at a cylinder of height h. It's held at 0 on both ends and some function g of z along the height h, and it has a radius b, I should mention as well. So we're looking for the steady state temperature distribution inside the cylinder shown. Again, that's something we've been doing throughout the year in BVPs, so nothing new there. But so expect a solution with no theta dependence. This is important because given that we have no boundary conditions or anything like that relative to theta, we right away need to expect that the solution will only depend on r and z. Otherwise, we're going to have an indeterminate problem because we'll have way too many coefficients to solve for without enough boundary conditions. So anyway, like I mentioned, we have our boundary conditions here. Phi of R0 is 0, phi of RH is 0, and phi of BZ is G of Z. So straightforward there. What we're going to go ahead and do is something, I mean, it's what we've been doing for a lot of BVPs throughout the semester. We're just going to go ahead and do our separation of variables, given that we have a homogeneous problem here. So we have 5RZ is equal to some function big R of R times some function big S of Z. So yeah, pretty straightforward there. And then we're going to go ahead and plug that into the cylindrical coordinates form of Laplace's equation, like I have up here. We're actually looking at Laplace equation, steady state temperature distribution. So the cylindrical coordinates form is given by 1 over R, d over dr, r, d big R over dr, plus d squared phi, or actually, sorry, this should not be r, it should be phi. d phi dr over d squared phi dz squared is equal to 0. So this is really just the cylindrical coordinates form of the Laplace equation. I believe this is given on the useful info sheet, but I would definitely double check that, and if it's not, it's definitely something you should know. So have a look at that. But anyway, we're going to go ahead and plug in our separated variables here into the equation. We get simply enough S over R, D over dr, R dr dr, plus R d squared S over dz squared is equal to 0. Now, again, as we have been doing many times, we're going to multiply through by 1 over Rs, just to rewrite this a bit in a more trivial form, where we'll be able to see like the eigenfunctions right away. So we get 1 over RR, d over dr, r dr over dr again, plus 1 over s, d squared s over dz squared is equal to 0. Straightforward enough. Now, again, we're going to just flip that onto the other side and equate it to lambda, as we always do with separation of variables, is equal to negative 1 over s d squared s dz squared is equal to our lambda. Now, for this specific problem, we're going to want to take lambda is equal to positive mu squared. Again, this isn't always trivial which one you need to decide, but definitely I would remember for this specific problem 10A, you got to take the positive lambdas. The more problems you can remember kind of which lambdas you take is going to help you a lot. Definitely, it just comes with practice, I think, and obviously you can't remember all of them, but the more you can remember, the better. So obviously in this case, we see the left-hand side here is not so trivial right away what we can do to solve that. It's a bit of a messy eigenfunction equation. So we're going to look at the right side here, and we actually just get that d squared s over dz squared is equal to negative s mu squared. And again, I should mention from up here, we have our boundary conditions. If you look at these two, we can actually write that as s because they're only in terms of the height z. So we have s of 0 is equal to 0, s of h is equal to 0. Straightforward enough. Now you should realize essentially this is just BVP1, and it should be pretty trivial to solve. Sn of z is equal to an sine n pi z over h. Again, h is our height there, so straightforward enough. If that isn't straightforward, I would definitely recommend you review kind of the earlier BVPs. This specifically is BVP1, but I think all those BVPs that are kind of get recycled a bit in the later BVPs are important to have like really down quickly at that, because the exam is probably going to be quite long, and it's important to not to trip up over those things. So to continue here, we have lambda then based on this is equal to n squared pi squared over h squared. That's just based on kind of, again, BVP1 stuff, but how we defined it as positive here, we still have it positive. That's what we want. Now, obviously, we need to look at the left-hand side, and this is where it's going to get a bit more tricky. But we'll have 1 over r dr is equal to n squared pi squared over h squared. So, like I said, this isn't the most trivial to solve right away, but once we understand how we're going to leverage the Bessel's equations, it should hopefully catch on a bit quicker. But so yeah, I'll actually write that out right now, the Bessel's equation, just so we kind of get an idea for it. So the modified Bessel's equation of order 0 is written as x d over dx of x dy dx minus x squared y is equal to 0. And that's the modified Bessel's. Like I said, the ordinary Bessel's I think is used for 10b or c, and that one uses regular Bessel's. I believe the only difference is that you have a plus here, but I would double check that. I'm not exactly sure. So, and this is equivalent to x squared y double prime plus x y prime minus x squared y is equal to 0. Obviously, that's just done by solving the product rule here and taking the derivatives. So nothing too crazy. But and then really what's important here is that the solution to this equation is given as b I naught of x plus c k naught of x. So these are just the functions that solve this equation. Obviously, this is something that is either needs to be given on the useful info sheet or you need to remember. There's no proof that goes into it that's kind of required here. You just need to know it. So yeah, important. But basically what we want to do now is to try to get a form for this that we can really just equate it to this and be able to plug into our solution. That's the goal here. And the way we can really do that is first we're going to multiply through by r squared r, just because as we see here, we want to have just like an x here, and right now we have 1 over r, so that's no good. But if we go through with that, we have r d over dr, r dr dr is equal to n squared pi squared over h squared r squared r. Yeah, so pretty good. Now what we want to actually do is a bit of a transformation of variables here. Obviously, like I said, we want to try to transform into this form. That's not going to be doable with our current variable definitions. So we're going to go for letting n pi r over h equal x and keeping just r is equal to y. Now what that's going to do is actually transform d over dr is equal to d over dx times dx dr. Sorry, dr. Sorry about that. And really, this is just a question of applying the chain rule here to transform the variables here. We have n pi over h over d over dx. Sorry about that. And yeah, really, like I said, that's just a question of taking the dx dr is just n pi over h. Straightforward enough, hopefully. And then also we can write r d over dr is equal to n pi r over h d over dx. And again, now we need to realize that this is actually just x dx. So, and you'll see that's pretty much exactly what we wanted. Now we're going to go ahead and take this back here and see what we can do with it. So if we replace all of those formulations that we just defined here in terms of x and y only, we actually get to and we're also going to bring this on the other side, I should mention. So we actually get to the exact form that we wanted. We'll have x d over dx times x dy dx minus x squared y is equal to 0. Yeah, and I mean, hopefully you can kind of see it from here. R dr is just x d over dx, so that's what we get here. Same in the brackets here. And then n squared pi squared r squared over h squared is just x squared, based on this definition here. So we got exactly what we wanted here. Now, like I said, we're able to quote this solution here to the modified Bessel's equations, which is fortunate for us because otherwise this problem would just not be solvable without that solution given. So if that isn't on the useful info sheet as well, it's definitely important for you to remember it. Oh, so I would double check that this solution is given on the useful info sheet. Otherwise, it's something that you should remember because you'll get stuck on this problem if you don't know that. So anyway, what we can say here then is that y is equal to b I naught x plus c k naught x, as I said. We can just go ahead and plug in the variables we defined. Y is obviously just equal to r of r, and we'll say n as well, just so we can right away get values for every value of n. Bn I naught of x is just n pi r over h plus c k naught n pi r over h. So yeah, we've definitely gotten somewhere now. We have our full formulation for Rn and Sn. Only thing we want to do now is really notice that we can eliminate one of these coefficients here, Bn and Cn, based on the properties of these two functions here, I naught and K naught. So basically what you need to remember is that limit as r goes to 0 of K naught of n pi r over h is equal to infinity. And obviously we don't want to have that. We want to have finite temperature distributions. So we need to say that Cn is equal to 0. And this obviously just gives us that Rn of r is equal to only Bn I naught of n pi r over h. So again, this is a property that you kind of need to remember here. And I know it's not the most trivial thing, but it's important. And I think the best way to show that is just showing the graphs of the functions. Obviously, there's no way we can just like plug in a value and see that. But so this is actually what the functions look like, I naught of x and k naught of x. And as you can see here, k naught of x goes to infinity as x here goes to 0. In this case, our x is n pi r over h, but same thing really. So yeah, Once we have that, then we can just go ahead and plug back into our initial formulation here. So we had phi is equal to Rs. So we have phi n of Rz is equal to Bn. Actually, I'll go ahead and say Dn right away. We're going to combine the coefficients here like we always do. We have Bn here and An here. So An times Bn is just some other coefficient Dn. So we have dn I naught n pi r over h sine n pi, z over h. Now I'm realizing I said h, sorry. There might be, no, actually, what am I, sorry. There's nothing wrong with this. This is correct, n pi z over h. And we should be pretty much good to go here. So now we have our full formulation for phi. We're going to just, as we always do, apply the principle of superposition, since we're looking for the null space of a linear operator. So that's really just going to be summation n equals 1 to infinity of the exact same thing. N pi r over h sine n pi z over h. So what we can do now is just apply our initial condition here. We have phi of bz is equal to g of z. So at the outer radius of the cylinder, we have the temperature distribution given. So what we're going to do is phi of bz is equal to summation n equals 1 to infinity of dn I naught n pi b over h sine of n pi z, z over h. That is just equal to g of z. Now, what we're able to do here, obviously we're not given an actual function. This is just a general case where we're just given some arbitrary function g of z, and so we're going to leave our answer in the form of integral. But you want to realize here that we're actually just looking at a Fourier sine series, essentially. And so, as we always do, we're able to write that dn I naught of n pi b over h is equal to 2 over h integral 0 to h of gz sine n pi z over h dz. And yeah, so I mean, if we were given a function here, g of z, we would have to go through with this integral. Probably takes either a u sub or an integration by parts, so it'd be a bit tricky. But in this case, we're just given g of z as an arbitrary function, so we're gonna be able to leave that as an integral for our solution. Same goes for the exam. If you only have some arbitrary function g of z, obviously you can't compute the integral, so you're good to leave it as that. So then you can really just say dn is equal to 2 over h I naught n pi b over h integral 0 to h g of z sine n pi z over h dz. Now that defines dn for all values of n. And we get our final solution, which is just phi of Rz is equal to summation n equals 1 to infinity dn I naught n pi r over h sine n pi z over h, with dn defined as above, obviously. Again, it's okay to leave your kind of answers divided like this. You don't need to arrive with an answer that just covers 2 lines because you try to plug in all the coefficients. But yeah, so that's pretty much it for BVP 10A. Hopefully that gave a good idea of how you kind of use the Bessel functions and their associated solutions to be able to solve a problem that otherwise you can't solve. So yeah, that'll be it for this video, and I'll see you in the next one.